this is NBER is something that we all kind of want to. How many people are familiar with that program? Or I should say, how many are not? How many are not? So, okay, so we're going to play around with NBER, and partly those of you who are not familiar with it will figure out how to do it. But then the other thing is, in the process of playing around with it, we're going to illustrate some ideas that I think are fun to talk about. So now we're going to be talking. That is to say, we're going to be talking more applications now. So let's get into the new Keynesian model to use as a vehicle for carrying this stuff. The new Keynesian model is now king. There is no other model. The only understanding that people have of, I'm going to keep saying things until somebody objects. The only existing framework for thinking about what's been going on for the last couple of years is this Keynesian framework. There is no other framework. The fundamental language, the fundamental concepts, the fundamental fears, the things that policymakers, when they wake up in the middle of the night and they are terrified of things, that image that they're afraid of is something that's articulated by this new Keynesian model. We may get into that as we go forward today, or if you like me to explain that more, we can talk also about it in breaks. In any event, I'm going to talk about the simplest version of that model now, what I'm going to do is I'm going to derive the nonlinear equilibrium conditions of that model. We need the nonlinear conditions if, for example, we're going to study what's called Ramsey optimal policy. Now, some of you will be familiar with that already, some of you are not. Either way, we'll be more precise about what that is in a moment. In fact, even if we want to study Ramsey optimal policy by doing linearization, we need the nonlinear equilibrium conditions associated with the model, and you'll see that. You'll see that when we get into that. So the nonlinear equilibrium conditions of the new Keynesian model, which are not typically written out, and some of you may not have seen them before, are very important. We're going to derive those. Let me maybe explain here what Ramsey is useful for. One is for defining the output gap, one of the most, possibly, maybe the most important concept in macroeconomics is the output gap. Where is the economy relative to where it ought to be, should be, something. The output gap. And in order to define the output gap, you have to define. Well, it's not hard to define where you are. You just go measure GDP, but you have to define where you ought to be. That's the other part of the output gap. And one definition of where you ought to be is the Ramsey efficient equilibrium. So Ramsey will be used to define the output gap. And when we talk about a positive model for the positive version of the new Keynesian model, I'll be using a Taylor rule, and we'll need an output gap in there. In order to find that output gap, I need the Ramsey equilibrium. So. Then also, if we get at the end, which I don't think we will, we talk about the timeless perspective and various other things that we need, and we want to do Ramsey optimal policy in real time, then we also need Ramsey, and we therefore will need the nonlinear equilibrium conditions. Of course, it's obvious you need the nonlinear equations, you need the actual equations of the equilibrium if you're going to do higher order perturbations like we talked about at the beginning. So that's another reason for that we need I don't know why the word nonlinear has to be added. We need the actual equilibrium conditions for the model as opposed to the linear equations that most of you are familiar with. And then the other thing we're going to do is study the properties of the new Keynesian model using NBER. We'll show various properties of that model. I'm associating with Claire de Galli-Gertler, but it probably should be Woodford too. I'm not sure the right thing. I always put this reflexively, but I'm sure that's not correct. Exactly correct. It's certainly a model that they emphasized in their famous papers in the late 90s. Okay, so the model is that there's a representative household that maximizes this utility function of consumption and labor, and then there's this preference shock. And the budget constraint, this is the simple model, so there's no capital in here. We'll be able to illustrate tons of great stuff with this model. I urge you, everyone, to, in your back pocket, always leave a little space for this particular model. As questions come up, you can pull it out and answer them even while you're riding on the bus or just hanging around, not sure what you're doing. This model is a fantastic model to ask all kinds of interesting questions, and many of them are, the answers you get do generalize actually to the more thing. So one of the equilibrium conditions associated with this model is the first order condition here for labor, that the cost of working, which is the utility cost of working measured in consumption units, has to be equal to the benefit of working, again measured in consumption units, which is the real wage. Then we have the intertemporal Euler equation. Of course, this is a nonlinear equation, so there you go, nonlinear equation. You have the intertemporal Euler equation, that's this equation here. I will have occasion to look at the linearized thing, so let's just quickly write that out. So that in the log case, we have the consumption growth here, and then write this everything in terms of logs like that, no problem yet. Now I just committed a crime. I moved the e through the exponential operator. Of course, this is a convex function, the exponential operator, so there should be another term here, a positive term, but it's very small, and I'm going to ignore it, and I'm appealing to the first order approximations as actually justifying that sort of thing. There's a little term missing here. It has to do with the variance of the one-step ahead uncertainty in these variables, which is a tiny, tiny, tiny number in macro variables like that. And take the log of both sides, and then we have this intertemporal Euler equation that the expected change in consumption has to equal the real interest rate. Okay, but still, this is the nonlinear equation here. That's the approximation. There's a tiny approximation involved. And I'm going to use this equation a bunch. So this is the log linearized intertemporal Euler equation here. We'll be using that equation more later. So, okay, there are some final good firms here. This is the basic structure of this model. They buy all these intermediate goods. They buy them at prices PI, then they sell them, and then the final good producers sell Y at price P, and they use this production function here. This is their profit function here. They use this to produce this stuff, and here is their production function. So this is the standard kind of setup here. Then the first order condition for these characters gives you the demand curves that the suppliers of the ith good are facing. You put all those Euler first order conditions into the production function, you get this aggregate condition on prices. This is an equilibrium condition. The prices have to satisfy this relationship here at the bottom. This is one of the nonlinear equations that characterize the equilibrium. We're going to try to compactify this down to 6 equations, but that's certainly one of, when you start at the large set, this is one of the equilibrium conditions. So the intermediate good firms, they face the demand curve. They realize that if they raise the price on their good, then the final good firm will buy less of it, and so on, according to that pattern there, and that's their demand curve. The technology that these people have is this simple linear production function. And notice I specified the growth rate of A to be a positively autocorrelated AR1 process. One of the things we're going to see is whether it's the growth rate or the level of A makes a huge difference for really good economic kind of reason. It makes a huge difference to the dynamic properties of this model. Then we have that there's the Calvo price setting frictions, that the ith firm either optimizes its price, sets it to a price PT tilde, or just this, there's a typo here, this should be the lag price, or alternatively they set their price to the lag price, lag value of their own price with probability theta. The P tilde doesn't have an I index in it because every intermediate good firm has the same state, and so when they optimize, they make the same decision. So that's why there's no I over there. Okay, that's their problem. One of the equations, it's variables that's going to matter a lot in this problem, is the marginal cost of these firms. Like if they were just, there was no price setting frictions, given the constant elasticity demand curve, they would always set their price equal to a fixed markup over marginal cost. So marginal cost would matter if there were no price frictions, and then with price frictions, marginal cost still enters the picture. So marginal cost is an important variable, and I'm going to define this thing, lowercase s, as the real marginal cost of production for the ith firm, which is, well, the usual thing. The numerator is the cost of an arbitrary selected input. In this case, there's only one input. So it's the cost of a worker divided by the productivity of a worker. That's the thing up there. I'm imagining that the cost of a worker is the real wage, but they're getting a subsidy. For reasons that are too boring to go into in great detail, I'm going to set up this model so that at least in the steady state, all the equilibrium allocations are efficient. The model has two sources of inefficiency, the new Keynesian model. One source of inefficiency stems from the assumption that there are price setters. That is to say, from the assumption that there's the monopoly power that you need in order to rationalize price setters. That price setter, that monopoly power causes them to restrict output and makes the aggregate level of output too low. That's a drag on the economy, keeps it away from being efficient. That inefficiency we're going to remove by subsidizing these guys. I mean, what we really should do is pass a law that says that you dare restrict output, we shoot your ass. But what we're actually going to do is we're going to give them a subsidy to produce the amount that they're supposed to. Of course, the second source of inefficiency in the model has to do with the price-setting frictions. The price-setting frictions have the implication that if aggregate prices are moving around, because some prices can't move and others can, it means that there are price differences in the economy. And when there are price differences, the given amount of labor is not allocated equally to all these production activities, and because of that, and because of this production function here has the property that if you have, say, 100 workers, and you allocate them equally to all the tasks, then you get the most out of those workers you possibly can. If you have 100 workers and you allocate like 4 to this I and 50 to that I and 60 to, well, you can't do that, it doesn't add up to 100. But if you don't allocate them equally, then you get less Y. So there's two sources of inefficiency. One is the price frictions, which cause a misallocation of resources and cause you to get less final output than you might otherwise get. And the other one is the inefficiency coming from monopoly power. And this economy is going to be set up in such a way that if the shocks are all turned off, eventually all those inefficiencies disappear. And so the first step I'm going to have in doing that is I'm going to subsidize these guys in order to, and I'm going to subsidize them exactly at the right rate so that we get the efficient outcome. Okay, so this is the definition of real marginal cost, and it includes in there the subsidy that I'm giving these people. The firm is required to satisfy whatever demand materializes at its posted price, and so the only decision this firm really has to make is how to adjust its price, and that's going to deliver other equilibrium conditions. However, they're kind of a pain in the butt, these conditions, because of this weird Calvo friction. So let's have a look at that. So here's the problem of the intermediate good firm. We know, by the way, we know what the answer is going to be in the end, is that they're going to set their prices as a function, the guys who are optimizing are going to set their prices as a function of marginal cost today, tomorrow, and the future. They're going to look at marginal cost for all time because they realize there's some chance that that price they're setting today is going to be the price they were going to be stuck with tomorrow. If there was no chance they would be stuck, they would just set price equal to a markup over current marginal cost. They wouldn't care about future marginal cost. But because they know they might be stuck with their current price, they'll care about future marginal cost. So that's going to be the ultimate answer here. But we have to get it in a compact form that we can stick into a computer. So here is the objective of the firms. This is their time T plus J profits. This is their costs. Notice there's no I in this cost. cost, because of the linearity of their production function, the marginal cost for every single firm is independent of how much stuff it's producing. There's no I in there anywhere. And as a consequence, when you look at the profit function, there's no I inside this S here. There is an I there. That's how much they produce. And then this, of course, this is the aggregate price index that reflects simply that this S is defined as having been divided by P. So this gives you the nominal cost, and this is the nominal revenues, and this is the value of profits to at the date T plus J. So that's their objective. And the ones that are maximizing that objective are only worried about the future states of the world in which they're stuck with the same price, which means there's only there's a subset of paths through the future event tree that they worry about, and that subset of paths has probability theta j. That's the probability that. So their objective, they can ignore all the other paths where their prices change. So the guy who's optimizing and choosing PT tilde is looking at that objective there, the one with the theta to the power j. So this expectation here includes all the idiosyncratic expectations about adjusting prices. That expectation only involves the aggregate uncertainty, and the idiosyncratic uncertainty is incorporated by the theta plus theta to the power j there. Okay, so now we just work this thing out. They're required to satisfy the demand curve. So that's the first thing I did, was I substituted out the demand curve here, and I get this expression. I got rid of the yi and substituted it out using the demand curve. Then I differentiate with respect to the price they're trying to choose, and then we get some nasty looking expression. Turns out to reduce down to this thing here. Then the next thing is we work with that expression a little more. That's just a copy of the previous one, and you end up with, in the end, this expression here, where I have divided, where I've defined this little price, this little p tilde, which is the ratio of the actual price they choose to the aggregate price. So there's a little kind of an inflation term that has to show the p. So this guy here, to write this guy in terms of this, you need an inflation term to take into account that this t plus j is not equal to t. So you've got the same ratio here, and this involves the inflation term. So this is just a rewrite of this first order condition. And having rewritten that, there it is, we can now solve for p tilde, and p tilde is just the ratio of the, you're just looking at the future marginal costs, which is exactly what you expect. These guys are setting their prices today as a function of the discounted future marginal costs, so it's a ratio of two things. This is not convenient, this expression, because it involves an infinite number of variables, and when you type stuff into, whatever, Diner, you can only type in a finite number of variables. So we have to write this, we have to express, so we got this price that they're setting in terms of a k and an f, but that's good news, because there's only two variables. The bad news is k is an infinite order present discounted value. However, there's a simple recursive representation for that stuff. You start at the top over there, write out what k is, and then you do a bunch of substitution, take into account the recursive form of this x guy, and you go and you scramble, and then you lose a little lime. You sprinkle a little lime on there. Lime is the law of iterative mathematical expectations. And then you go like that, and then boom! You see that you got the exact same thing on the right that you had on the left, except at a different date. So we got a recursive formulation for this thing. So it only involves that present discounted value can be expressed in terms of a very small number of variables. There it is. And then the denominator, I want to get rid of marginal cost, so we can do it in that way. The real wage, it'll be important for us to notice this a little bit later. So that real wage is equal to the marginal cost of working, again, denominated in consumption units. So that's been substituted up there. And of course, this guy here is going to cancel by the construction of the subsidy. Okay, so what we get is that the price is the ratio of those two things, that the numerator is this recursive thing, and the denominator but is the same recursive thing. You don't have to go, it's actually a little bit simpler. So there's f is just this. So we're now getting that into some very simple variables. But this little p tilde, we're going to get rid of that too. The name of the game here is let's get this to a small set of equations. So I need we have equations that characterize optimization by people, but we still need we need the aggregate consistency conditions here that we don't have. We have individual optimization, but we don't have, like, I don't have anything that looks like a resource constraint. I don't have anything like the price restriction across prices and stuff like that. But by the way, one of the things that's tricky about this model is that there is no aggregate resource constraint, which is the regrettable thing. There is not a simple relationship like, for example, that yt is equal to e to the a times n. We don't have something called an aggregate production function in this model. What I mean by an aggregate production function is an equation that relates aggregate outputs as a function just of aggregate input. Why don't we have that? Well, as I said earlier, the distribution of inputs matters. If this economy was efficiently organized, we would never contemplate the possibility of unequally distributing labor across sectors. But because we have these price-setting frictions, that will happen all the time. The prices of intermediate goods that are low are going to attract more labor. Prices of intermediate goods that are high are going to attract less labor, and so there will be all the time. And so there's no relation. That would be the relationship if all the laborers were allocated equally everywhere, but in practice they will not be. And so that is not, for example, the production function in this model. So let's get into this stuff. Let's talk about the price relationship here. So if we look at we got a problem here because we have an infinity of prices, and infinity of variables is not a good idea with this sort of stuff. So if you look at this infinity, you can see that there's a subset of i's of the i's associated with firms that optimize, and then there's the other subset of the ones that don't optimize. Now, the beauty of the optimizer ones is that they're all setting the same price. So this is just a constant times the fraction of those people that there are. But this is one nightmare-looking thing, because this thing will have a whole distribution of prices in it, because there are some people that changed their price yesterday. They'll have one price yesterday. There are other people who haven't changed their prices for 2 periods. They'll have a different price, and so on. So the ones that don't change their price, they come in every shade and color and size. So anyway, So here we have the first substitution here is, it comes down to there, and the real issue is this one here. And in principle, when you have models like this, you actually have to characterize the distribution of those prices, and because that will matter for what that integral is. And then you also have to characterize the law of motion for those prices, how it goes from one period to the next, and how it's perturbed by realizations of shocks. That's what the problem you're facing, in principle, you would face. However, and this is why the word Calvo, I guess it's the name Calvo gets attached to this stuff, is that there's something very simple about those prices, which is they were drawn literally at random from the population of prices yesterday. The whole Calvo price stickiness mechanism is a random mechanism. No matter who you are, your probability of getting your price, being allowed to optimize or not optimize your price is the same, which is it sounds like a terrible assumption, but it delivers a thing. Because if what that integral is doing is you're integrating over a random selection of people from the population. So let's take as an example, suppose we go to a large population, India or China, and there's a distribution in those countries of men by height. There's a true distribution of men by height. Now suppose I go to China and I pick 300 million Chinese 200 million Chinese males totally at random. And I ask, what is the distribution of those males? And how does it of their height? Well, how does that compare to the actual Chinese distribution? It's basically the same. Basically the same. I mean, if I had been selecting, I'm only going to choose males that are like, 4 months old, or, if there's some selection thing, but no, if you take them totally randomly, and the ones you selected have the same distribution. So the distribution of the PIs that are in that integral is the same as the distribution of all the prices in the previous period, because people are randomly selected to be stuck with their old price. And that's fundamentally the reason why that integral looks a lot like the same integral of yesterday's prices, i.e. yesterday's price. So this is what that integral looks like, although you have to shrink it down by theta. Now normally I would have like 17 more slides to explain this, but that's the basic insight. It's because of the random price setting that this equation here, which is a nightmare, this equation, this aggregate price equation up there, is one nightmare equation. It's not clear how you're going to integrate that into your computer program. Because these people were randomly selected to not be allowed to change their price, that integral turns out to boil down to just yesterday's price. So now we only have two different distinct variables, P tilde and P. Now I'll do a little division. This is a linear homogeneous equation, divide, no problem, and boom, I got an expression in terms of the inflation rate. It's a nonlinear expression in terms of the inflation rate and the price of the price setter guys. There's a simple connection between those people. Okay, now this is the thing for the prices, the price relationship. Let's have a look at output. So technically, as I said before, there's no aggregate production function in this model. There's no rule that says, okay, we got this many inputs, this is how much aggregate output you're going to get. There's no such equation. You don't know by knowing how many people are working what output's going to be. And that's because of the price frictions. Now, Tak-Yun wrote a paper in the JME which explained what I'm now going to show, a wonderfully simple argument that he made, which, although it can't be that simple, because when he first did his thing, people were whispering, he has a mistake, there's a mistake. And that mistake, Tak-Yun. And so he didn't actually get a lot of action on the job market. Actually hurt him big time. That's a mistake. In rumors. And so people initially couldn't understand what the hell he was talking about. But now it's actually, his name is in bold print. And I'm going to describe his argument for you, and you're going to wonder, why would even smart people say that there was something wrong with what Tak-Yun did. Now, he did this in a much more general setting with capital and stuff, but the basic logic is no different from what I'm doing here. Anyway, so what Tak-Yun was, he derived the aggregate relationship between outputs and inputs that take into account the fact that you need to know something about distributions. So what he did was he said, okay, let's just define this crazy variable y star. No real economist would actually talk about something like y star, because notice I'm adding up over the intermediate inputs. These are different goods, and I'm not weighting by the prices. So it seems like a mistake right off the bat, but let me do that anyway. So I'm integrating over the prices. Of course, this is a wonderfully simple relationship, because if I substitute in the production function, this thing really is A times N, because I'm just adding over everybody. On the other hand, that's not aggregate output. It's not adding over things. Aggregate output doesn't add. It adds weighted by prices, or it adds through the CES function, whichever you want to do. It's the same, actually. So then the next thing I do is I take the demand curve, and I substitute out the yi in terms of the demand curve. And and then I guess I shouldn't cough too loud, because blow your ears out a little bit. And then I take the demand curve and substitute that out, and I write this in that form. And the next thing is I'm going to define this object as P star. I mean, it looks a lot like, see, the actual expression for the aggregate price index looks a lot like this crazy thing here, except it has a different power. So I'm going to call this thing P star. This looks kind of like the thing, but it's not the same. It's a different weighted average of all the prices, P star. And this thing will have the same law of motion. This is Mr. Calvo steps in over here. This weighted integral involves a fixed number of things on one hand, but then all the non-changing prices on the other hand, but the Calvo insight still works, and we get a very simple expression for the Mr. P star here. So if we just go over here now and turn this stuff around a little bit, because y is the variable of interest. Y star is something that only a non-economist would ever think of doing, because it's adding up things, apples and oranges. Turn it around, and you get this expression here, and then express this as a lowercase p, and presto. Now what you've got is a relationship between aggregate output and aggregate inputs that's distorted by something, and that something has to do with differences in prices. What does that mean? Well, look at the numerator. It's one weighted average of all the prices. The denominator is a different weighted average of all the prices. And what you can show is that all the prices are the same. By the way, they're linear homogeneous averages. So if all the prices are the same, then P star over P is 1. And if there's any kind of difference among the prices, then P star, now this part's not so obvious, then the P star over P is less than 1. P star over P is a function. This little P star guy is a function of the distortions among prices, and it has this feature here that it's always less than or equal to 1. It looks a little bit like, I don't know, you guys have probably heard, you surely have not heard, of Okun's gap. No one here. Has anybody here ever heard of somebody named Okun? No. You don't want to admit that, though. So you have to be a little older to know about Okun. So Okun's gap, see? In fact, this corresponds to an idea that people used to have all the time, and it seems to me it's still a good idea. I don't know why they got rid of it. There was an idea about economics that the way economies work is they chugging along and they're kind of efficient, and boom, all of a sudden they go down. Then they come back up again. Boom! The Great Depression was viewed as an example. That's why they do trend through peaks. Has anybody ever heard of trend through peaks? You calculate potential GDP by doing an envelope of actual GDP, and that's that idea that the economy is kind of normally chugging along okay, and then those drops that we see are inefficiencies, actually fits in nicely with that kind of whole thing. Bob King used to call that the Okun's gap variable. The problem is that, in fact, it doesn't move very much. When you actually plug in plausible parameter values, it doesn't move very much. But it's an interesting thing. The inefficiency, it's a one-sided inefficiency. It can only go down, and it has a max of 1. Okay, so let's bring these equations together. I'm going to give you a bunch of equations here. So here's that number 1 there is one. I'm going to give you 6 equations that characterize the private sector equilibrium. Equation number 1 is the numerator in the price setter guy equation. Equation number 2 is the denominator in that equation. Equation number 3 is this thing here. So remember, this is P tilde equals that thing there. I'm going to get rid of P tilde and replace it by K over F, because we got that from the first order condition. The first order condition of the firm setters gives you one relationship for P tilde, and then the cross price restriction gives you another relationship for P tilde. Substitute them out, you get this as K over F is equal to this thing here that involves inflation. And another equation here is the P star equation. That's the equation. So you get that from here. By manipulating this thing here, you get a nice little recursive expression in the nominal prices, and then by just dividing by big P and converting this to the little p guy, you end up with this equation here for the price distortions. This is a law of motion for the price distortions. It's an absolute miracle. You don't need to know anything about the distribution of prices among individual people. All I need to know is I need to know what yesterday's price distortions were. I need to know what the current inflation rate is, and that tells me what today's price distortions are. You see, there's nothing else in that expression there besides inflation and lagged price distortions. Maybe you can also see that that pi bar is the aggregate inflation, it's the gross inflation rate. So if there's no inflation, that pi bar is equal to 1. And maybe it's too much to see, but that's a stable difference equation. if there's no inflation, eventually the price distortions go away. But they can't go away right away, right? But they will eventually go away, because eventually everybody gets to change their prices. And so eventually what will happen is that, see, when there's no inflation, then suppose nobody's changed, suppose all the prices are the same and there's no inflation. Well, then all the prices will remain the same. If the prices are different and there's no inflation, then the adjusters will be moving in the direction of making all the prices the same, and eventually they become the same. Okay, whatever. So here's the intertemporal condition for the households, and there is the aggregate inputs and outputs, and boom, we now have 6 equations in 8 unknowns, which is actually a little bit disappointing because it sounds like it's too few equations. But it's not disappointing because, number one, notice I've included nu as an unknown, which was kind of crazy because I already told you it was 1 minus f, so I overcounted the number of equations. And does it bother you that we're short one equation? Suppose this was 6 equations and 6 unknowns. Would that bother you? It would bother me because I haven't said something. This is an economy with an interest rate. I haven't said anything about monetary policy. There's a relationship I've left out of the stinking thing. It can't possibly be closed. There's another equation that's knocking at the door and wants to come in too. And if we could solve the model without that equation, it would be a sad thing for that equation. So, so it's actually not surprising that it's 6 equations and 8 unknowns. Number one, and I'm not sure why I left the nu in there as an unknown. And number two, well, I know why I left it in as unknown. You'll see in a second. And number two, it's clear that I've left out something, monetary policy or something like that. I've left that out because I got this nominal interest rate here. So the system, in effect, is still underdetermined. But it's not underdetermined because I forgot something about the private sector. The private sector is a closed system here. We've got enough equations and variables. It's underdetermined because of something on the outside that I left out. So in some sense, we have 2 policy variables here, the interest rate and nu. And so I'm going to now describe 2 ways to pin down those 2 policy variables. One is I'm going to pin them down by supposing that policy is chosen optimally. And the other way I'm going to suppose is that policy follows some rule, like the Taylor rule. Now, it's going to turn out that I need as an input to my Taylor rule, I need something called the output gap, and that will involve optimal policy. So in order to even think about the Taylor rule, I'm going to have to think about the optimal policy first. So we're going to do that now. I'm now going to talk about Ramsey optimal policy. I now have an economy. I've completely characterized the private sector equilibrium conditions, and but I have one or 2 degrees of freedom, depending on how you count, whether you include the nu or not. The 2 degrees of freedom, so there's kind of like 2 degrees of, you got 8 variables and 6 equations. It's like you have multiple equilibria. You know what I mean? There's like many settings for the 8 variables that satisfy the 6 equations. And what optimal policy is it's the setting for the variables that's best among all the possible settings. So I guess this is what I'm saying here. And so the Ramsey optimal thing is to choose the 6 variables to maximize utility, but satisfy the 8 equations, or whatever. No, sorry, 6 variable. 8 optimal setting of the, no, a little typo here. It should be 8 variables. I guess you can't do that. Well, you can, but all right. This is cheating in some sense. I know people who would not do this. They would say it's wrong to change that. Once you put that 6 there, you have to suffer the consequences. Anyway, so it's 8. So you have 8 variables, and there's a space. So think about an amoeba. If I would draw a big thing, and there's a space of possible values of those 8 variables, which is defined by the 6 equations, and I'm going to go looking in that space for the best setting for those variables. And we'll define that problem as a simple Lagrangian problem. There it is. So the Ramsey problem is to choose to try to get the highest utility, to go hunting through this space of possible settings for the 8 variables to find the point, the setting for those variables that has the highest utility. So it's a maximization over, see the max there, there's 8 variables over there, and I'm maximizing utility subject to my 6 equations, my 6 private sector equilibrium. And that's called a Ramsey problem. By the way, this is the way, although I mentioned this once to Lars and he denied it, Lars Svensson, and he denied it, but I'm going to claim it, and he's not here now to deny it. This is the way Lars Svensson does this at the Riksbank. We'll take all the private economy, he takes the Taylor rule out of here. If you have a Taylor rule in your back pocket, when you walk in the Riksbank, they have a special Taylor rule detector when you go, and they will remove it from your pocket. You're not allowed in the building with a Taylor rule. So these systems are underdetermined, and so the way they compute policy, the way they solve the models, is they solve models this way. No Taylor rules allowed in the picture, so the systems are fundamentally underdetermined, and so when they solve a model, they're finding the solution to the Ramsey problem. Although not with one major proviso, which is that the utility function of the agents in the model is not what's used up there. The utility function of the governing council, actually that's not the right word for it, the governing council, the analog of the governing council at the Riksbank is put up there instead. So they're picking in the set of all the possible equilibria, the one they privately prefer the most. And that may not be the same as the representative agent's utility function. By the way, is there a rationale for that? Well, I'll give you a hint. It begins with the letter R. But that's too difficult. So the next letter is O. Ro. Okay, I'll give you 3 letters. R-O-G. Rog. Okay, R-O-G-O. Yes! Rogoff. So that perspective on policy is that it's actually a desirable thing, for reasons that are not included on this slide, to appoint a central banker who does not have exactly the same preferences as the public, and it's a desirable thing to have that central banker at work in your central bank. And in any event, I don't know what Lars Svensson's view about this is, but in any event, what they do in the Monetary Policy Committee is that they in effect have to figure out a way to aggregate their preferences. And it's actually an interesting discussion exactly how do they do that, and they do it in a very interesting and intelligent way. They'll write down, so then it's not technically a Ramsey problem, because Ramsey always refers specifically to the social welfare function up there, but it's mechanically, of course, the same thing. You're maximizing some criterion, slapping on multipliers on all the equilibrium conditions that are given to you by private economy optimization, market clearing, et cetera, et cetera. And notice we're putting in the actual equations here, including Tak Yun's adjustment down here, and including, of course, also the law of motion of that adjustment. Okay, now there is one constraint in here which is so stupid you just have to get rid of it, which is the linear constraint on the resource, on that C. That's just a linear constraint. I mean, anybody who solves things, they see a linear constraint, that's out of here. Anything linear is out. So I just substituted out. See here, we got the N, there's the N and the P star, because there's log C up there. And then everywhere this thing is written, you got all this stuff going on. So actually a more sensible way of thinking of the problem is this way. Now, so this is a Ramsey optimal policy problem. This problem has actually quite a maybe shockingly simple solution, which actually gives us a little bit of insight into the whole model here. So, for example, look at the first equation, lambda 1. Okay, so let me ask you the question. Is that a binding restriction? Is that a binding restriction? Is there something about lambda 1 that inhibits the ability of this problem to maximize the criterion? Okay, notice that inside lambda 1 there's a variable RT. Notice the variable shows up nowhere else. It's not in the utility function, it's not in any of the other equations. So somebody who's maximizing this thing is saying lambda 1, that's a stupid constraint, because I can always choose RT to just make that equal to 0. In particular, we expect that lambda 1 is 0. We expect that it's non-binding on that problem. Now let's have a little peek at some of the other equations. For example, lambda 3. You might conjecture that lambda 3 is also non-binding because you could just use it to define f. What the hell? And f doesn't appear, well, it does appear somewhere else there, but we can make lambda 5 non-binding too. Now the p star equation, not obvious that'll be non-binding. In fact, it's binding. In fact, intuitively it's binding. If I see that there are big distortions in prices today, can I achieve the no distortion state tomorrow, say if I'm the monetary authority? Yes or no? The answer is no. Why? The answer is that's 150 zillion targets you're after. If you want to make all prices the same, that means you got to make this price equal to that price equal to that price. That's too many targets, and there's only 2 degrees of freedom in this system, R and nu. So you're not going to. All you can do is you can't. So this thing is going to be the p star intuitively. It has to be binding thing, but it has to be binding because it also restricts how much you get to consume. So p star matters. It's in the utility function, and so on. But by the way, one of these times I'm going off, so I might as well say goodbye now because I won't have the opportunity. Okay, so we can conjecture that. We can think of the lambda 1 as simply defining R, the guy there defining F. The lambda 4, we can just think of that as defining nu. Then you might say, oh, nu is a constant. Fine, make nu a function of t. Think about nu as a function. It'll turn out that nu being a constant was just fine. And you can think of that, so conjecture would be that actually this problem boils down to this thing. That this problem boils down to that thing. That it's that optimization problem, and that's a staggering problem. Because notice, first of all, there's nothing forward-looking in that problem. There's nothing forward-looking in that problem, which tells me that the Ramsey optimal policy is probably going to be time consistent in this. There's no forward-looking variable, so there's no reason to say, oh, I'm going to do this in the future, and then not do it. Because there's no forward-looking variable that you're influencing by any such announcement. So, in any event, there's the maximization. Now, you can think of this as a conjecture. I'm conjecturing that all those multipliers are 0, and then we could verify ex post that, in fact, that conjecture was correct. By the way, if we go back to this thing, are there any circumstances where you think it's obvious that ex post that conjecture was not correct? Yeah. Yeah. That's exactly the one that I had in mind. Now, I don't have the inequality constraint in R on there, so I probably should have written it in, and then it would have been true that wouldn't have been necessarily, that might have been a binding constraint. So, in effect, I was assuming the 0 bound not really very relevant, which it kind of isn't in a neighborhood of the steady state of any kind of reasonable model where you'd have 2.5% inflation, so the nominal interest rate would be 2.5% higher than the real interest rate. So it's But you're totally right that that's a little bit So if you were solving the model, you would want to check to make sure that you're computing positive interest rates. And if you're not, then you have to slap that on as an extra constraint. And then actually life gets more hard than what I'm about to do here. So you calculate the first order condition. This is a very simple optimization problem. Calculate the first order conditions, you end up with this. Then you do a little bit of scrambling around. You get this simple little law of motion for the price distortion. And then you end up in the end with this simple solution. This is the solution to the Ramsey optimal problem in this case, which is that the price distortions evolve in this particular way. The inflation rate is not going to be 0 right away. what happens is that, well, the price distortions are going up towards 1. Well, they can't go, yeah, obviously they're not going to go down. That would be kind of weird. I mean, why would you get, crazier or something? In any event, they're going to go up from low to high to 1. They're going to asymptote to 1. But the fact that they're rising means that the inflation rate is, tomorrow is higher than today, but tomorrow's in the basement. So the inflation rate is going up from below. Did I get that right? It's very hard for me to think up, down, sideways. I'm much more straightforward. Positive number, I can't think of numbers in denominators. But if P is bigger than P, PT is bigger than P minus 1, it means that, whatever, you can figure this out. There are definite implications for inflation. The level of employment is that thing there. By the way, that's an interesting result, that the level of employment is that thing there, because this is the first best level of employment. You can easily work out that if you bring in a planner here who never heard of markets, who never heard of private ownership, who never heard of any of this thing, who only sees utility functions and production functions, that planner would choose that thing there. Notice the planner does not involve responding to technology shocks because income and substitution effects cancel here. They do respond to negative preference shocks because when people get backaches, it's a good idea for them not to do that. The solution to this problem involves setting the subsidy in the way I did earlier anyway. And then consumption is equal to this expression. And eventually, asymptotically, consumption will be equal to its efficient level, because asymptotically, the solution to the Ramsey problem involves getting rid of the price frictions altogether. You can't get rid of it in one period because there's too many targets, but over time you can get rid of it. Here's a simulation of this law of motion here. I started at of the P star equal to 0.8, and then I simulated it up, and it's a monotonically stably converging thing up to the number 1. So the solution to the Ramsey problem does not involve going to zero inflation instantaneously, and it does not involve getting rid of price distortions instantaneously, but it involves getting rid of those things kind of asymptotically. So, and when you get there asymptotically, you get to the first best level of consumption. You're always at the first best level of employment. I'm going to refer to the Ramsey allocations as the natural things. So the equilibrium of the Ramsey is the natural equilibrium. There's some, among people, there's a difference there. Some people say that some people like to call the natural equilibrium as the flexible price equilibrium. I'm referring it to as the natural equilibrium. The natural equilibrium is the Ramsey equilibrium. What I mean by that is that the natural equilibrium is what you would get if you had optimal monetary policy. Not what you get if you have flexible prices, because flexible prices, that's part of the technology. I don't want to ask, what would the world be like if we had flexible prices, because that's part of the technology. I mean, if I was allowed to play with technology, I might as well just say, make the endowment economy. I could say, let's get rid of the production function. Why do we have to work so hard all the time? Just define natural output as what you get from an endowment economy. Well, of course, that's goofy, but getting rid of sticky prices is analogously goofy because it's a reduced form thing, but it's a reduced form for something. And just assuming it goes away, I'm not sure what that means. So I'm defining the natural equilibrium as the equilibrium that's associated with the efficient monetary policy. It's an achievable equilibrium and so on. And the fun thing about this is that it's time consistent. There is nothing about this policy, the Ramsey optimal policy in this model, that would make the planner later, if they re-optimize, come up with a different decision. Basically because the binding constraints are only forward-looking in this thing. Or put differently, there's one distortion, there's two distortions and there's two policies, you can nail them. There's no advantage to surprising people. Timing consistency comes from advantages to fooling people, but there's no advantage to that here because their two instruments are enough to get them to the efficient outcome. Okay, if we had sticky wages, then the Ramsey problem is not time consistent anymore. All right, okay. But I guess I should pay attention to the time. So what time do we break for lunch? Okay. Now that has to be a binding constraint, because presumably, yeah. Okay, so here are the equations for the new Keynesian model under the, Ramsey optimal policy, the natural equilibrium. And I've written them in log form. So this n star is the log of employment. It's equal to this. In the natural equilibrium has a wonderful property in this model that it's independent of A. And that will be very useful for intuition later. It's a very useful benchmark. It's a property of the fact that I've assumed balanced growth preferences here, and that there's no intertemporal technology, so that the cancellation of income and substitution effects, which with capital would only occur asymptotically, happens every period, at least in the efficient equilibrium. So n is a function only of back pain, not of A, of little a. And then this is output is a function of little a, because n is not a function of little a, so output responds 1-for-1 with A. But then, of course, it also responds to back pain because people are working less when they have back pain. Now, in the natural equilibrium, remember the natural equilibrium is an actual market equilibrium, so we can define market prices and inflation. Those are all well-defined things in the Ramsey equilibrium. So there's also going to be an intertemporal Euler equation. Well, all the equations are satisfied here. And there's the linear representation of the intertemporal Euler equation in the natural equilibrium. In the Ramsey optimal equilibrium, it's that thing there. It's the same thing that we got in the first diagram long time ago, the first slide a long time ago, although I didn't have stars on stuff. And actually, I think I had C over there, but now C and Y are the same thing in the natural equilibrium, because I'm imagining enough time has gone by so that P star is equal to 1. So in the natural equilibrium at the very beginning, P star is not equal to 1, but I imagine that time has gone by enough, so P star is equal to 1. So that C and Y are the same thing in the natural equilibrium. And inflation is, I see I've got the phrase eventually. I'm assuming we're in the eventual situation. All right, so now we can get a very simple expression for the natural rate of interest. The natural rate of interest is the interest rate in the Ramsey equilibrium. And by just substitute out for Y star here, now that's just exogenous variables. We have one endogenous variable here, R star. We can now solve for R star. There it is. R star is equal to that crazy thing there. Now, that expression is wildly important in this model. So if you look at R star, notice that it's positively related to delta A. If the growth rate of technology is positive today, it means that R star is going up. Why? What's the intuitive reason for that? So R star is the interest rate. That's the net nominal interest rate. Which of course the same in the natural equilibrium as the net real interest rate, because inflation is 0 in the natural, because we're assuming that the initial period has gone by. So R star is the nominal interest, or the real rate, whatever you want to think about in the natural equilibrium. And why would it be related to positively to delta A? Well, because I've assumed that delta A is positively autocorrelated. So if there's a positive delta A today, it means that A is going to be higher in the future. But in this economy, C is proportional to A. As A goes up, C goes along with it. So if people see a big delta A, it means they're seeing big consumption in the future. And, but that's the future, not the present. It's like, you're approaching Christmas time. That means you can open your presents in the future, but you're not supposed to open them today. Consumption today is equal to today's A, not tomorrow's A. You might want to consume more. You're going to have more A in the future. You might want to consume more today, but that's not the efficient thing to do. Oh, why not? Why isn't it efficient to open your presents before Christmas? In this model. If A is higher in the future, it means the productivity of labor is higher in the future. If you try to consume more today like in the future, why is that not a good idea? Huh? You have to work more, and it's not very efficient today because A didn't go up today, A went up tomorrow. That's what we're talking about. So the R star has to be high in order to discourage people from doing this inefficient thing. They want to, because of log utility, they want to go to the bank and borrow and so on and so on. But the efficient thing, and we're talking about the efficient equilibrium here, is to discourage that by raising the interest rate. By the way, that interest rate is very important because if you think about the monetary authorities as their policy as picking the interest rate, well, R star is really it's really, the thing that if they did it, they would achieve the right thing. So that R star has a very special status. I mean, in the case of in central banks, at some level, that's all anybody ever talks about. They may not use that language, but they're always saying, oh, what should I do with the interest rate? What does that mean? Well, one way of thinking about what that means is I want to make the interest, where's the natural rate to which I should be setting my interest rate to? Okay, so now notice here that lambda is less than 1, so tau is a negative coefficient. What the heck's that all about? Well, when tau jumps, then consumption is going to be low. And where does tau go in the future if it jumps? The tau is is assumed to be a first-order autoregressive process, so if it jumps, it comes down again. It's going to dissipate, as opposed to A. If A goes up, it keeps on rising because it's delta A that's positively autocorrelated. But tau is a stationary thing, so when it goes up, it'll come down, which means that when my consumption goes down, it's going up in the future. Did I say 1 minus tau lambda is a negative number? I think I did say that. But it's not. It's a positive number. Because lambda is a number that's less than 1 in absolute value. So it's a positive number. Positive. 1 minus lambda is positive. So why would you raise the interest rate when tau goes up? Why? Why? When tau goes up today, consumption is low today, but where is it today compared to tomorrow? Well, tomorrow they're not going to have so much back pain, so consumption in the future will be higher. We're going off a low base, but still by comparison, and so people want to bring that future higher consumption to the present, so you have to raise the interest rate to get the efficient allocations, because the efficient allocations involve low consumption today, high consumption in the future, not efficient to consume a lot today. Why? Because people have back pain. They don't want to work. It's painful. Not a good time to raise consumption. So it's inefficient. Okay. All right, so now I've described the natural thing and natural stuff. So the natural, you can think of natural output would be Y star, and the natural rate of interest. These are all the objects in the natural equilibrium. And now we go back to the new Keynesian model with the Taylor rule and put everything together. So I'm going to rig up the Taylor rule so that in the steady state, inflation is going to be 0. I'm going to rig it so that if you turn off all the shocks, the Taylor rule will deliver a 0 inflation rate asymptotically. Of course, if we have a 0 inflation asymptotically and we set our nu the way I said we're going to set it, then what happens is that asymptotically we have an efficient equilibrium. That has big advantages technically, which I don't want to talk about. I could talk about it this afternoon if we did the Ramsey optimal policy, but we're not going to do it this afternoon, so we could discuss it separate outside. Okay. So I'm going to rig the Taylor rule and the financial variable, the new thing, in such a way that asymptotically, if you turn off the shocks in the model, it's going to go to the efficient equilibrium. And all the problems are going to have to do with responses to shocks. So now we get the famous New Keynesian IS curve. So we know that in the actual equilibrium, the log linear approximation to the intertemporal Euler equation is given by that thing over there. We derived that from the first period, except I had not y, but c. I had not y, but c, but it's consumption, right? Consumption comes out of the intertemporal Euler equation because it's the marginal utility of consumption that's in there. So the derivation many slides ago had y, not c. Now, is there a difference between y and c in the equilibrium, in the actual equilibrium? No. There's nothing else to do with output other than consume it. So they're the same thing. So when we derived it for c before, we did it for y as well, because c is equal to y. That's the basic resource constraint. Where things get confusing is when you relate y to aggregate inputs. Okay, in the natural equilibrium, we get that equation over there. That's the Euler equation. Inflation is 0, so you don't see it in there. Now subtract the 2, boom. There we get one of the standard sort of equations in the new Keynesian model, which is you get the output gap, you get an intertemporal Euler equation in the output gap. And it has this funny natural rate hiding inside of it. Well, it's happening because we took the difference of the two. So, I mean, often analyses of the new Keynesian model will begin with this equation, just write this thing down in terms of the gap, the natural rate of interest, but we didn't do that. No, we couldn't do that. That would be too easy. If we look now at the output in the new Keynesian equilibrium, the aggregate output relationship, of course, in the equilibrium, y is equal to log of p star plus n plus a, where p star is the thing that we've been talking about, okay? So now this deserves a little bit of discussion, this p star. I don't have a diagram to do this, so you're going to have to visualize this thing. On the horizontal axis, I've got price distortions. On the vertical axis, I've got p star. And, wait, do I have a picture of this? I don't think I do. No, I was planning to draw this. So distortions are over here, and and then in the middle there's no distortions, where all the prices are the same. So at that point, p star is equal to 1. And then as I go away from 1, the thing comes down. So it's a mountain like that. Now in this model, in the steady state, what are the price distortions? The Taylor rule makes inflation 0 in the steady state. So what are the price distortions going to be in the steady state? Suppose that everybody kept their prices constant. Is that feasible? Yes, because the idiots who aren't changing their prices, well, they're not changing their prices. The clever people who are changing their prices, what are they doing? They're not changing their prices either. So if you have 0 aggregate inflation, because the non-optimizers are doing 0 inflation on their own prices, in that case, all the prices will be the same. So if we think about this diagram, where are we in the steady state? Well, in the steady state, we're at the point where there's no inflation, so we're at the top of this mountain. There's a one vertical axis is p star, and then if you have a memory like mine, like if you see something, it's like gone almost immediately. Like goldfish apparently have a memory of 3 seconds. So when I draw this figure, if you're like me, you see it, but as soon as my hand is done, it's gone. And in actual fact, it is gone because it's just in the space there. Anyway, there's p star over here, and then there's the distortions here. And at 0 distortions, you're at the top, and then you come down both ways. No matter what's happening in the distortions, if they go this way, that way, whatever, they're always coming down. Now I'm going to give you a little hint. Mr. Takyun, he said that the relationship between distortions and the p star is differentiable. So suppose I have a curve that reaches a top over here, and it's differentiable, and it comes down over there. What's the slope of it there? 0. Suppose I do a first order approximation of that curve there in steady state. 0. It's a straight line. The slope is 0. It's just a constant term. So if you do first order approximations, because we're assuming that the non-optimizers are not changing their prices and the steady state inflation rate is 0, because of that one thing, because the price distortions are efficient at the steady state, the p star to a first order approximation is just equal to 1. And it's not changing. It's not changing in a neighborhood. Now, if we change any one of those assumptions, like if we made inflation 2.5% per year, and we made the non-optimizers not change their prices, well then the steady state will be over here, and the slope, there will be a slope there, and then you would have the P star would be a living, breathing, biological creature that evolves and has to be included in your equations. But as long as you're supposing that in the steady state there are no price distortions, to a first order approximation, you can pretend that it's always equal to 1. So, now by the way, you might want to check that. How would you check that? Well, you just type in the nonlinear equations that we did here, go to Dinaire, do a second order approximation, see if it makes any difference. And I tell you right away what the answer is going to be. It makes no difference for the types of fluctuations you see in the United States. So the first order stuff really is first order, and the second order stuff actually is second order. So anyway, so the first order approximation, so to a first order approximation we can ignore this. Oh, by the way, let me say something. When we do Ramsey, well, I can't do that. Okay. So now we have a simple, in this first order approximation, I have this is my resource constraint. I now actually have an aggregate production function. I can write y as a direct function of the aggregate labor and the aggregate technology. Okay, then there's this whole nightmare of equations here associated with price setting. You got the numerator, the denominator, you got all those equations associated with price setting. You sit down and you take a linear approximation to all those equations, take out a big soup spoon, and you stir. It might take you several days because you're going to make so many mistakes. You'll make more mistakes than there are lines on the page. And anyway, you keep on stirring and stirring and stirring. You keep stirring, and eventually you're going to start asymptoting to this. This is the expression here. So this is the standard little guy here. And the amazing thing is that this guy doesn't just come out of nowhere. It comes out of here. And one of the things that's vital in the derivation there is that the inflation rate in the steady state is equal. There is no, that prices are efficient in the steady state. So if you have an inflation rate, that you have the non-optimizers are raising their prices by that inflation rate. That's crucial for this derivation here. Anyway, so one of the equations, so what do we get out of this? So far we got this little guy here. We got this, they call this the IS curve. Then we have an aggregate output relationship because of we're doing a first order approximation, which allows me to ignore, to set P star equal to 1, so the log of P star is 0. And then I do the linear approximation on that. This of course takes a little bit of work. It's not obvious by looking at it, but you do it and you end up with this expression. Oh, I guess there's a derivation here in this handout. And then here's my Taylor rule. So the Taylor rule, this is in logs. So the thing at the left-hand side is the interest rate in the actual equilibrium. It's a log of it's a net interest rate equals alpha times the interest rate in. And then you have, this is the whatever. This is pi, I guess you can read this too. And then this thing here is the output gap. So I'm imagining they're looking at the output gap. This is kind of a standard thing that people write. I must say, I have no idea what they mean by this, because if you knew what the output gap was, then you could probably calculate what the natural rate of interest was, and you wouldn't have to do any of this Taylor baloney. But any event, so I got the top output gap in there. To compute the output gap, I need to know what the efficient level of output is in the economy. And it's not obvious how to figure that one out. Okay, so here are the equilibrium so here are the equations. This summarizes all the, if you go back and look at the equations that I had at the very beginning, I had 6 equations and 8 variables. One of the 8 variables I nailed by just making nu efficient. All of those equations have been worked with in order to get down to these equations here. This Phillips curve actually summarizes a whole bunch of equations, the equations on this earlier page. This is three equilibrium relations are summarized by this Phillips curve. Of course, we substituted out f, and we got rid of a bunch of variables. Oh my God! I didn't know that letter G does that. So, and then okay, there's the policy rule, the IS equation, and then this is the natural rate. One thing that's kind of fun and surprising about this thing, there's a bunch of things about this that are kind of weird. Let me just tell you, because none of you know about real business cycle models, probably. Me, I think of that as like the standard model. But slowly as time goes by, no one remembers. Like the dinosaurs. Who remembers the dinosaurs anymore now? No one. And the same thing with a real business cycle model. Anyway, a real business cycle model has kind of three equilibrium conditions. There's the intertemporal Euler equation, resource constraint, and maybe the labor equation if you have that equation in there. It's like three equations. Those three equations, you could completely describe and discuss them in about 34 seconds. After 34 seconds, you're just repeating yourself. There's just nothing there. There's no economic, there's like just trivial stuff. This thing here, I actually didn't even do all the talking I could do without repeating myself to derive these equations. These equations involve a huge amount of, it's three equations, well, it's actually four. It's four equations, but there's an immense amount of stuff behind these equations. Anyway, I'm not sure why I said that, but I just did, so it's too late. And there's another interesting thing about this, which is that in the model there are two shocks, tau and A. And if you look inside here, you know, you look at the actual equations, the Phillips curve, the IS equation, you don't seem to see it anywhere. Where the hell are those things? Well, they're all kind of sneaking in through this little R star. Now, I can't tell you why I find that interesting, I'll admit, but it's just it's a weird thing. You know, you'd have thought it'd come in a more blatant way, but they're all coming in through the natural rate of interest in this model. Now that I say it, I realize it's not a very interesting remark. I wish I hadn't said it, but it's too late. Okay, now let's solve this model. So we don't have to linearize it anymore because we already linearized it. When you work with NBER, you'd actually type in the actual equations. And, well, actually, this afternoon we'll type in these linearized equations. Well, we won't type them in because I already typed them in for you. But we'll have these equations here. I'm pretty sure that Jesus will have examples. He has a real business cycle model example, so he's going to have the actual equations, and then NBER will do the linearization. And we're going to plug these things in. So we have the actual equations, so we don't have to linearize them anymore. We did linearize them, but now I want to set them up and solve them. So I'll use the canonical notation that I used at the beginning, well, at the end of the previous kind of lecture or whatever. And here it is. I took all the equations, and I write them, and these are the variables whose values are determined at time t. So this here is zt, inflation, output gap, R star, all these things, and this is t plus 1, blah, blah, blah. Then we also have some shocks in here, S, these are the exogenous shocks, this is the law of motion. So this guy here is this equation here. And so now what I want to do is I want to find a solution. So there it is. There's the whole system is there. That upper equation is all the equations on the previous slide. And then you have the law of motion for the shocks. And now the solution is a matrix A and a matrix B that satisfy the equations I put up before. Now there's one thing that's kind of fun about this, which is that if we go back and look at the system, notice that there's one equation here that's got this one lonely little guy. In fact, if you look at this, you'd think this is all zeros. You wouldn't even notice that. You know, he's after you notice him, you realize he's there kind of feeling bad and lonely because absent this one thing, it's all a bunch of zeros. So in particular, if we look at this system here, this alpha 2 here, if we set alpha to 0, this alpha 2 would be equal to 0. And if you look at this, can you see a solution? If alpha 2 is 0, how many people in this room would need a computer to find a solution to this thing? Okay, a equals 0 is a solution in that case, which kind of makes sense because the system is so profoundly internally dynamic or something, because there's nothing in the economics. If this alpha 2 is 0, there's like nothing backward looking in this system, so it's not surprising if the solution would not be backward looking either. Now you still have to worry because Mr. NBER will get all upset. Mr. NBER, see, is a very serious person. And Mr. Diner, remember what I was saying, is they're going to take that polynomial and they're going to put it up they're going to stick it up all over the wall, all the a's that satisfy that equation. So the fact that you know that one of the solutions is a equal to 0 doesn't mean there can't be other ones. So we know that I shouldn't say a, because that's a. A solution to this thing is a equals 0, but there may be other solutions. We still have to worry about that possibility. But it's kind of obvious that in the case where there's no endogenous persistence, and if we get rid of the endogenous persistence in the Taylor rule, where is the Taylor rule here? If we get rid of this guy here, then there's just nothing that's backward looking in this system, and then A is 0, and then Z is simply a function of the current realization of the shocks. And all of the persistence of Z, of the endogenous variables, is coming 100% from the persistence of the exogenous shocks. Okay, so let's, it's 12:15 is the time. Okay,